In this video, I'm going to take you through how to convert non-exact differential equation to exact differential equation. In our previous classes, we've learned about exact differential equation and the condition that should be satisfied before an equation will be called an exact differential equation. So if those conditions are not satisfied, then the equation will be non-exact. But there is a way of converting it from non-exact to exact, and that is what we are going to do in this video. Watch me to the end so you understand every part of the video. Every exact equation is to satisfy d of m xy over dy should be equal to d of n xy over dx, where the general exact differential equation is represented as m, a function of xy attached to dx, plus n, a function of xy attached to dy, is equal to 0. So once this condition here is satisfied, our equation can be called an exact differential equation. If not, it is a non-exact differential equation. So in this video, our interest is to identify some non-exact differential equation and convert it to exact differential equation. Let me take the first example. I have y prime is equal to 2xy minus x. This equation here, we can straight away say it's an exact because it is not in the exact standard form. We should express it in this form where the dx will be attached by a function of what? Xy, and the dy will be attached by a function of xy. So we have to separate the dx and the dy. You know that this y prime here is the same as dy over dx, right? This is equal to 2xy minus x. At this point, I'll cross multiply to get dy multiplying 1 is equal to 2xy minus x multiplying dx. Once I have this, you know exact differential equation has a term to this side. So I'm going to have negative of 2xy minus x dx plus dy equals 0. And at this point, this one has been expressed in the exact standard form. But before we conclude that it is an exact standard form, we first need to check this condition here. If it doesn't satisfy this condition, then we say this equation is not exact. So let's see, where is our m of xy? M of xy is a function attached to the dx at all times. So in our scenario, it is equal to negative of 2xy minus x, and our n of xy is equal to 1. At this point, I'm going to differentiate my m of xy with dy. So d of m of xy over dy will be equal to, if I differentiate this expression with respect to dy, this is a constant, it will tend to 0. And this one, I'm going to have negative 2x. So I'll have negative 2x because when I differentiate, the y becomes 1. When I differentiate my n of, so d of n of xy with respect to dx is a constant, so it's obviously equal to 0, right? So since my d of xy over dy is not equal to d of nxy over dx, my equation is not exact. Now it is non-exact. How do I convert it from non-exact to exact? At this point, I use my general rule, which says that you need to find 1 over either m or n. So let's use a 1 over m. So 1 over m multiplying the expression, our d of m xy over d of y minus d of n xy over d of dx should give us a function which is in what? In terms of what? Y, g of y. So whenever you divide 1 over m by this expression, you should get a function in terms of only y. If this condition is satisfied, then you are going to have the integrating factor for our non-exact to be equal to the e to the power integral of negative, so it's going to be a function of y, g of y dy. So at this point, let's move straight. So we have this to be negative 2x, this to be 0. And what is 1 over m? So in this case, let's consider the second part. The second part is saying if this one was to be 1 over n, if this was to be 1 over n, then we should expect a function in terms of x only. And our integrating factor in that scenario is going to be e to the power integral of what? G of x dx. So take note, if here becomes 1 over n, where n is a function attached to the y, it's expected that it will cancel the y term. Sorry, if here becomes 1 over n, we are expecting that it will cancel the y term and it will be left with the function x alone, and the integrating factor becomes e to the power integral g of x. But if here becomes m, then it will cancel the terms which are what? X. So for that reason, you should get a function purely in terms of what? Y, and this becomes the integrating factor. In our situation, let's see. So always find this expression. You subtract this from this. So we are going to get negative 2x minus 0. And what is that? The answer is negative 2x. From negative 2x, we can see that if we divide it by our n, here it is 1 because there's nothing here. It tends to be simpler. For that reason, I'm going to have 1 over n formula, which is the 1 here. And I'm expecting a function which is in terms of x only. So now my 1 over n becomes 1 over 1 multiplying negative 2x. And that is giving me negative 2x, right? So my integrating factor becomes e to the power integral of my g of x dx. And this equals e to the power integral negative 2x dx. If you have this, what are you expecting? You should expect e to the power negative s squared, right? And that is simple integration. So this becomes our integrating factor. Once you get your integrating factor, what do? You simply multiply it through the expression. So we have the expression of negative 2xy minus x dx plus dy equals 0. I'll multiply this through, and I'm going to get negative 2xy minus x multiplying e to the power negative s squared plus dy multiplying e to the power negative s squared equals 0. So now this becomes the converted exact differential equation of the question given. Once you get your integrating factor, you only multiply through by your equation, and now this becomes what we should expect. Now let's see the second problem. I have y squared dx plus xy dy is equal to 0. At this point, I'm to check if it is exact. This is my mxy, which is y squared. My n of xy is what? Xy here. So I'll find d of m of xy over dy, and what am I getting? 2y. Then I'm going to find d of n of xy over dx, and what am I going to get? If I differentiate this with respect to x, my y is a constant, and x will give me 1, so I get y. Hence, the difference between this, which gives me that expression, will be 2y minus y, and the answer is y. So once I get this y, I come back to check my n and my mxy and nxy. Which one, when I differentiate, or sorry, when I divide, it will be simpler. I got my difference to be y. So if I divide it by this, things will be simpler, right? So when I divide it, I'm expecting a function of only y. So I'm going to have my integrating factor. So let's see, I'll have 1 over m of xy multiplying what, y, and that is going to give me y over what, y squared, and that is giving me 1 over y. So as I said, once you get the function in all y, our integrating factor is simply equal to e to the power integral of negative what, g of y dy. And here I'm going to have e to the power integral of negative 1 over y dy. And this is going to give me e to the power negative ln y, and that will be what, e to the power ln of y to the power negative 1. Is that not it? So at this point, you know e to the power ln is the same as what, y to the power negative 1. So now my integrating factor is simply 1 over y. Hence, I'll simply multiply this through the equation, and I'll be getting y squared dx all over y, then plus my xy dy all over y equals 0. At this point, I'll get y dx plus what, x dy equals 0. Let's test if this one is an exact truly. When I differentiate this with respect to, I'll get 1. This with respect to x, I'll get 1. Hence, it is now exact, and our conversion is true. Thank you for being with me in this class. See you in the next class.